Today we will be discussing on three of the most primary elements in electrical technology. They are the resistors, the capacitors and the inductors. So, that is the basic objective in this lecture, to learn the function of the primary components in an electrical circuit. The lecture flow for this lecture is as follows. First, we will discuss the energy flow, how the energy flows from the source to the destination. This will be followed by a generalized description of the primary components. This will be followed by the discussion on resistor, and then the capacitors, and then this is going to be followed by a discussion on the inductors. Then later on, after discussing these three primary elements, we will focus our attention on the sources. Okay. So, let us now look at how the energy flows. Energy always flows from the source to the load. It emanates from the source and then terminates at the load. In the process of flowing from the source to the load, many things happen to the energy. One of the things that happens to the energy is that it can get transformed. It can get transformed from electrical energy to heat energy, from electrical energy to magnetic energy, or to mechanical energy, or to a translational mechanical energy, so on and so forth. There is something else that can also happen to this energy in the process of moving from the source to the load. It can get lost. Lost meaning that amount of energy becomes unavailable to the load. Further, this energy can also get stored, and it can get stored in two forms: the kinetic energy or the potential energy. These are the only two forms that it can get stored. So, here we see that the energy that gets lost, that becomes unavailable to the load, remains lost, but the energy that gets stored in either the kinetic form or the potential form can later be recovered and sent either to the load or back to the source. One of these things can happen, as you will see by and by in future circuits. So, the energy gets lost as heat in most of the time in a component called a resistor, which is denoted by the letter R here, and the energy gets stored in the kinetic form in a component called inductor, which has an inductance values as indicated by letter symbol L here, and it can get stored in the potential form in a component called the capacitor, denoted by the letter symbol C here. So, now let us look at these primary components one by one. The resistors first. What are these resistors? What are the features of these resistors? First of all, it is a non-dynamic or not a dynamic component. What does this mean? It means that it is an algebraic component. Whatever is there, the input comes at the output at that instant, at every instant, instant by instant. There is no history, there is no memory. It cannot remember the past states or the past values. And further, the most important functional property of the resistor is that it has to dissipate. It is lossy, and most of the dissipation occurs as heat. So, let us try to characterize the resistors. In fact, most of the components generally we characterize by the IV characteristic. We put the V voltage on the x axis, I on the y axis. So, here in this particular diagram, V is the independent axis and I is the dependent axis. So, in this IV characteristic, we plot the character of the resistor, as you see here, is a straight line, and the slope slope in this case is I by V is 1 by R or 1 by the resistance value. So, this is how the resistance is described. So, if you see here in this graph, if this line representing the resistor is aligned along the vertical axis, that is the y axis, then the slope is infinite, which means that R is 0, and this would represent short circuit. On the other hand, if this resistor line is aligned along the V axis, that is the x axis, then R is infinite as the slope is 0, slope of this line is 0. So, we see that the resistor line can vary from short circuit along the vertical axis to open circuit along the horizontal axis, and in between it can take any value from 0 to open circuit. This is the VI characteristic of a resistor, of a simple resistor. Now, coming back to this VI characteristic, let us take a point on the voltage axis and then draw a line directly up onto the resistor characteristic line, and from that intersection point we draw another line which intersects the current. So, at this point we see that voltage here gets multiplied by the slope 1 by R and results in the current. So, you have the voltage multiplied by this resistor resulting in this current. That becomes the governing equation for the resistor. I equals voltage by R, or it can also be written as voltage equals current into R. It is basically the same equation which is algebraically represented in a slightly different way. This is called the Ohm's law, one of the most fundamental laws in electrical engineering which you will be using almost throughout your life. Another important character in the resistor is its power dissipation, because we said that energy is going to get lost in the resistor as heat. We need to quantify how much amount of this energy gets lost. Power in watts is equal to voltage in volts into current in amps. So, VR is the voltage across the resistance and I is the current through the resistance. So, the product of this V into I will give you the wattage or the power that gets dissipated in this resistance. Now, this IV itself we saw by Ohm's law can be written as I into R, current into R, and into a further component of current which is equal to I square R. So, the equation for the power is I square R. The power dissipation can also be written as VR, and IR can be written as VR by R as we saw earlier in the governing equations. This gives VR square by R, that is voltage square by R. So, summarizing, we see that the power dissipation in a resistor can either be I square R if you know the current, or if you know the voltage across the resistance, then it is V square by R. So, you see here the summarization of the power. Power is VR into IR, power dissipated in the resistor is also I square R, power dissipated in the resistor is also V square by R, depending upon which variables are known at any given point of time. There are different types of resistors. One is the carbon composition resistor, the way it is made. You have the metal film resistor, wire wound resistors and such, and many more types. How does one know what is the value of the resistor of a given resistor. Let me show to you a resistor, how a practical real world resistor looks like. So, what you see here is a resistor which has two leads. There is one lead here, there is another lead here, which gets connected to your circuit, and this portion is the resistive portion which impedes the flow of the current, and there is going to be loss, the I square R loss or the V square by R loss or V into I R loss, any one of those equations. This is a carbon compound resistor, it is a half watt resistor. You see that there are some bands on the resistor here, some red band, violet, black, so on and so forth. The resistor value is recognized by the band, the color bands that are drawn on the resistor. Okay. So, the color coding is as follows. We see here on the slide that there are these numbers from 0 to 1, 0, 1, 2, 3, 4, 5, 6, 7, and each number has an associated color, which I am writing here. The 0 is represented by black, 1 is represented by brown, 2 by red, so on and so forth. 3 is orange, yellow, green, blue, violet, gray, white, till 9. So, each color here as given represents a numeric value. Now, it is pretty difficult to remember the order in which the colors are written. So, therefore, we normally have a key. You look at this first letters B, B, Roy, R O Y, G, B, V, G, W. Okay, these two are phrases, G, B and V, G, W. You can remember it as phrases. G, B is the short form for Great Britain, V, G, W is the short form for very good wine. So, you can remember the whole phrase, the whole color code as B, B, Roy, Great Britain, very good wine, which will give you the order, the sequence in which you can remember the color codes which represent the numeric values. So, how do we read the colors in the color code? Now, look at this resistor here. It is having, starting with the red color as its leftmost band, color band. Then you have the violet color band, and then followed by the black color band. And there is a fourth color band here, the extreme, right extreme, and that color band represents the tolerance, variation of the resistance with temperature. So, the value is given by only this first three color band. Now, the first band represents the first significant digit, the second band the second significant digit, the third band is the multiplier 10 to the power of something, whatever that color represents. So, here for example, if we take that particular resistance, you have the first band which is a red, the second band which is a violet, and the third band which is black. So, the first band red we put 2, the second band also gives you the next significant digit which is violet, which is number 7 here, 7, and the third band which is black is the multiplier which is 10 to the power of the numeric value of black, which is 0, because numeric value of black here is 0. So, the value of the resistor is 27 into 10 to the power of 0, which is 1, which is 27 ohms, and the symbol for ohm is the Greek letter omega. Okay. So, this is how you read the color code from the value of the resistor from the color code as indicated. The resistors are shown by various symbols in the textbook. You have a rectangular box with 2 leads, you have a zigzag set of lines connected to the 2 leads. This is one form of representation, and you have a rectangular box and then an arrow in between to represent a variable resistor, and also in this form a zigzag with an arrow as a variable resistor. These are the various symbols of resistors. Before we go into the new topic, let us look at some real world resistors. This is one of the resistors that you just saw while we were calculating the value of the resistors. It is a carbon compound resistor. Likewise, here is another carbon compound resistor. This is also a half watt resistor. You also have a look at this resistor size wise relatively. This is a quarter watt resistor. I will put in a different value of a different type of resistor. You see this resistor here. This is a box type. This is made differently. This is called a metal film resistor. This is more precise than this in terms of variation with respect to temperature and such, and they are generally used for frequency tuning components. There is another type of resistor here, slightly different from the type that you saw. This has 3 terminals. This is a variable resistor, just like we saw in the symbol here, 2 terminals and an arrow in between. It is that component. You have 2 terminals, and the third terminal is the tap which represents the arrow, which varies with respect to either of the 2 terminals. There is a screw here which can be rotated to position the center tap value at any arbitrary value depending upon the particular circuit. So, if we connect a voltage across these 2 extreme terminals, the voltage across that is going to be fixed, because the resistance across the 2 extreme terminals is fixed. And if we rotate the screw, the center tapped position keeps varying, and the potential of the center tapped value with respect to its extreme terminals keeps varying, and therefore, we say the potential is varying with respect to the extreme terminals. And this is called a potentiometer. It is a variable resistor. Apart from these resistors, there are other resistors also which are bigger in size to handle higher wattages. Now, here is one such component. This is also a potentiometer, similar to the low wattage blue box that you saw previously. This also has 3 terminals. These 2 are the extreme N terminals of the resistor, and this center terminal is the center tap, which actually will vary with respect to the N terminals, and the variation of the center tap can be attained by rotating this vertical knob which is around here. There is this another type of fixed resistor. This is also actually a carbon compound, but you will see that this is slightly bigger than the half watt and the quarter watt resistors to handle much higher power dissipation capability. These are the high wattage resistors which will go into your circuits. There is still higher wattage resistors available in the market. This is a 25 watt resistor. This is a wire wound resistor, and you will see that the value of the resistors are written on the body of the resistor, and here you do not see the color coding. In fact, in high wattage resistors there are no color codes, the value is directly written on the body of the resistor. Another high wattage resistor, which is actually of similar size compared to the 25 watt resistor that you saw just now, is something like this, which has a heat sink also. you will see the two terminals here and the value written on that one 100 ohms, and it is a 100 watt resistor, which is 4 times power dissipating capability than the previous wire wound 25 watt resistor, but of similar size. It is basically because of the heat sinks that is encapsulating the actual resistor and which can dissipate the heat more effectively, and this has 4 mounting holes which can be mounted onto another aluminum base plate or a base metallic sheet, which can dissipate the heat further much more effectively. Now, we shall look at still bigger resistors. In fact, these are not the limiting values of the power wattages of the resistors. In fact, in the industry you will see that the wattage of the resistors can be as high as even 1000 watts, 10,000 watts and so on and so forth. But let me show you a 1200 watt resistor which is variable, which looks something like that. It is pretty heavy. Okay. So, let me place it here. Okay. You see that there are 2 cylinders. Are you able to see? I will hold it like that. There are 2 cylinders composed of wire wound wires. This gives the resistors, they are connected in parallel such that they can handle higher current and therefore more dissipation. These can handle something like 25 amps and they are 2 ohms, which means something like 1250 watts. Now, there is a lead screw arrangement here with a center tap which can move around here. I can vary this knob here and therefore change the position of the center tap. Now, the center tap is connected to this knob here. Okay. The one extreme terminal is here, the other extreme terminal is on this side, and therefore, you have the 2 extreme terminals and the third center tap terminated here. Okay. So, this is also a potentiometer, but in the high power regions of operation, these type of resistors are called rheostats. You can also get fixed resistors of such high powers also. So, now coming back to our topic of the basic components, we were till now looking at the resistor component, the one which dissipates energy. And if we go back to one of our earlier slides of energy flow, we saw that we were focusing till now on this component which takes away the energy or the energy that gets lost in flowing from the source to the load, and that component is the resistive component. Now, let us look at the storage components, that is the kinetic storage and the potential storage. Let us first look at the potential storage component, which is the capacitor. So, now what are the capacitors? Comparing with the resistor, we see that the capacitors are dynamic components. What does it mean by dynamic components? Means it can remember, it has history, it can store the past states or the past values, it can have initial conditions. That is what a dynamic component means. It is not algebraic, its present is based on previous values, and therefore, they have memory. Now, the fundamental functional difference between the capacitor and the resistor is that this can store energy, whereas the resistor dissipates the energy, gives up the energy. So, this stores potential energy in the potential form. Okay. So, how does this store the energy? Let us look at a very simple analogy that we most of us would have seen in real world. This is a picture of a tub with an outlet at the bottom, and there is a tap which fills water, and the water is continuously flowing out through the bottom tap. Okay. So, the flow, inflow and the outflow can so be adjusted that there is a particular height of water which is built up, and this is the buffer water. So, this water that is getting stored in this bucket is something like stored potential energy, In fact, that is how the concept of the capacitor can be related to this particular analogy. So, we say that the input flow of water is something like input flow of charges into the capacitor, and that is called charging, and the flow of charges out of the capacitor or flow of water out of the tub is something like discharging the energy which is in the tub or which is in the capacitor that we are analogously calling. Okay. The capacity of this drum or bucket is analogous to the capacitance value of the electrical component capacitor, and the height or the head of water that is going to get stored in this bucket is the potential of the energy, and that potential is the voltage potential in the case of the capacitor. So, analogously this particular system which we probably see every day, bucket getting filled with water and then getting discharged, is will relate very well to a capacitance action. And the volume of the water is actually the charge that is put into the bucket or that is put into the capacitor. Now, the capacitor looks something like this in its most primitive form. It has two plates. There is one plate here, there is another plate here, and in between there is non-conducting dielectric material. Okay. So, the charges, let us say there is a current flow, the charges come and accumulate on this. Let us say they are the positive charges, and then it will induce equal amount of negative charges on the other plate, and then there is a potential difference between these two plates, which is the potential. So, this charge accumulation is called the potential storage in the capacitor, which has a capacity C. So, that is the metal plate as I have indicated. This is the dielectric, this is the capacitor with capacity C, and the charge Q is current into time. The current into the time is the amount of charge that gets accumulated here, and the difference between the potential at between these two plates is the potential V or volts. Okay. So, here are the steady state equations for the capacitor. The charge Q is related to the current and time in this fashion. The current into time is equal to the charge. The charge is also equivalent to the capacitance or the capacity of the capacitor into the voltage V. Q is equal to CV, Q is equal to IT. These are fundamental steady state relations. The dynamic equations, the steady state equation is when everything is under stable operating conditions, nothing is varying, nothing is changing. In dynamic conditions, when there are transients, when there are step changes. So, these are the dynamic equations which are the more general equations. Under steady state constraints, you will see the earlier steady state equations coming into play. So, in the case of the capacitor, the voltage across the capacitor is remembered by the capacitance. So, the voltage is the state value. The current through the capacitor is always 0 in the average value. The average value of the current is always 0 in the capacitance under steady state conditions, but under dynamic conditions you will see that it is given by this equation, I is equal to C dV by dt, or the voltage is given by 1 by C integral of I dt. It is exactly this equation written in a different form. Now, this integral here implies that there can be history, there can be initial condition. So, the initial condition as far as the capacitance is concerned will be a voltage value. So, therefore, capacitor remembers voltages, it can remember the immediate past value of the voltages, and voltage is the state value or the state variable for the capacitance. And in the case of the capacitance, the voltages cannot change suddenly, it can only change smoothly or continuously. There cannot be a discontinuous change in voltage because of this fundamental equation, the integral equation. The V here on the left hand side cannot have a step change. The energy storage equation, we saw that the capacitor is a potential energy storage component, and therefore, what is the amount of energy that gets stored in the capacitance, and that is given by E, the energy, which is equal to 1 by 2 C V square or half C V square. You see that the energy storage variable is V here, the potential of the, therefore, it is the potential storage component, half C V square, and that can be obtained by simple derivation. We know that the wattage is V into I, and V into I into time is going to be the energy, watt seconds. So, integral of that over a period of time or over a period will give you the energy which is as given here. So, we say that as the capacitor has the voltage variable here in the energy equation, and its state variable or the state value is the voltage, or the history that it can remember is the voltage, which is the potential, and therefore, it is called the potential energy storage component. The capacitors also come in varied forms, varied types. There are different materials that are used in the manufacture of capacitors. So, you have basically two types, broad categories of capacitors, the polarized capacitor and the non-polarized capacitor. By polarized capacitor, what I mean is that there are two terminals like in a resistor. One terminal should always be more positive with respect to the other terminal. So, that is a polarized capacitor. In the case of the non-polarized capacitor, either terminal can be more positive than the other terminal at any given point of time. So, there is no restriction that one terminal should always be more positive than the other terminal. In the polarized capacitor, the electrolytic capacitor is one which is most commonly used, and in the electrolytic capacitor there are two significant or more popularly used capacitors, the aluminum electrolytic capacitor and the tantalum capacitors. Tantalum capacitors are a bit more accurate in terms of the capacity. The aluminum electrolytic capacitors have lesser tolerance, meaning the variation is much more. It can vary from minus 40% to plus 100% than the value of the capacitor compared to the value of the capacitor that is written on the nameplate of the capacitor. In the case of the non-polarized, you have the capacitors named type named based on the material of the dielectric that goes into it, the ceramic dielectric type or the polymer based, you have the metallized polyester. Metallized polyester is something which is having very low tolerances to changes in the environment, and therefore, they are used for frequency tuning applications, things like that one. And this is the symbols that you normally encounter in the literature in the circuits, electric circuits for the capacitor. This is the most common symbol that you will encounter, two parallel lines with two leads coming out like that, and this is another symbol which is normally used for electrolytic capacitance, one with a thicker box type rectangular box type terminal, and another terminal which is a line. The box type has a plus there indicating that it is a polarized capacitor, that has to be always positive with respect to the other terminal. And then you can also have variable capacitors with the arrow indicating that it is a variable capacitor. There is also a capacitor with the following symbol, which you also will come across in the literature. A terminal which is attached to a straight line plate, and another terminal which is attached to a curved plate. This also sometimes is used for electrolytic capacitors, that is polarized capacitors, with the straight line plate indicating plus and positive with respect to the curved plate capacitor. This is also one of the symbol that you would be coming across more commonly. Let us now look at some of the capacitors that you will find in the real world. If you look here spread out, there are a few capacitors. The smallest one here, this is a paper capacitor, and unlike again as I told you earlier that in the case of the resistors you have the color codes for the values, for the capacitors the values are printed on the body of the capacitor itself. So, you need not remember any color coding for this. So, this is normally used for decoupling in electronic circuits. This is another ceramic capacitor. These are non-polarized. These are all non-polarized capacitors here, what you see on the front. This box type here is a polyester capacitor used for frequency tuning applications. This has very low tolerances, meaning it does not vary much with temperature. Now, these two black capacitors that you see, they are polarized. They are what you call the electrolytic capacitors, and they are specifically here in this case what I have here is aluminum electrolytic capacitors. They are very frequently used in power supplies for actually holding the charges. They can hold large quantities of charges and they can come in very large capacities. So, these capacitors are in general used for actually holding the charges, whereas these capacitors also do the same function of holding the charges, but their application is more for frequency tuning, decoupling, things like that one. So, this is aluminum electrolytic. You see there is one short lead and one long lead, that is to distinguish the positive and the negative pole. But even otherwise on the body of the capacitor there will be a plus or a minus sign with put near the one of the terminal to distinguish it from the other pole. This is slightly higher capacity capacitor, which is as you can see something like 4.7 microfarad written on the body. There is also another value which is written here, 100 volt. All capacitors, there are two things that you will see on the nameplate. One is the capacitor value in farads or microfarads or nanofarads or picofarads, that will be written. The second number or the value that you will see on the nameplate is the voltage that it can withstand, because beyond which the dielectric will break down and then you will see that it will get spoiled or it will get damaged. So, you should not apply a voltage to the two terminals which is higher than what is written on the nameplate. So, which means that this is a 4.7 microfarad 100 volt capacity capacitor, and you should not exceed the voltage of 100 volts here. Now, let us have a look at few other capacitors that are bigger in size. Why should the capacitor be bigger in size? In the case of a resistor, we saw that as the dissipation amount of heat that it has to dissipate increases, the size also increases. But here the capacitors are not supposed to dissipate, but still you see that they come in various sizes, right from small to the big. There are two things which are going to determine the size. One is the voltage. If you are needing to design a capacitance which is supposed to withstand a very high voltage, then also you need to have a dielectric in between which can withstand that field, which can withstand that voltage, and therefore the size grows up. Then another thing is the capacitor gets polarized, and if the frequency of that polarization is high, then the internal molecules or the polarization zones which keep alternatively polarized, depolarized, polarized in one direction then the other direction, that will cause some heat called the equivalent resistance or the equivalent series resistance in the capacitance, which will cause some heat to get lost. Even though ideally a capacitor is not supposed to lose any energy, a practical capacitor will always have equivalent amount of resistor which will lose the heat because of the polarizing and depolarizing effect of the charges in the capacitor, and this will in general be represented the equivalent circuit as a equivalent series resistance or an equivalent parallel resistance, whichever one may want to use. Okay. So, an ideal capacitor is not lossless, it has some loss in it due to this practical limitations. So, due to that the size also will vary. So, as the currents in the capacitor increase, the sizes will also go up because the ESR is going to dissipate that. Now, here is another non-polarized capacitor which can handle much higher current than the ones you just saw, and therefore, higher which means that higher current carrying capacitors should have lower equivalent series resistance or ESR. So, this is one such non-polarized capacitor normally used for snubber applications. I will also show you another capacitor. This is an electrolytic capacitor, polarized, of similar size. You see here the two terminals and see here the marking, the minus marking, which means this terminal which is closest to the minus marking is negative and the other terminal is positive. So, that other terminal should be more positive than this terminal. So, always look for a polarizing mark on the capacitor which says that that terminal should be either more positive or less positive than the other terminal. Let me show you something bigger. Do you see this capacitance? With some marking here. Now, this capacitance has leads on this side. This is an axial lead capacitance. It is 4700 microfarad capacity value. You see the minus sign here with arrow sign, which means this lead is negative, which means this lead should be more positive than this at every instant of time. So, this is a polarized capacitor. Similarly, there is another electrolytic capacitor which I just showed you. This is radial lead as against the axial lead here. So, in the market you will find these two types of varieties, the axial lead electrolytic capacitor and the radial lead electrolytic capacitors. The polarity is of course indicated here on this type. I will now show you one more capacitor which is still more bigger in size. Look at this capacitor. It has two terminals, okay, and this is a polarized capacitor. If you can see here, there is a plus mark, which means that this terminal has to be more positive with respect to this terminal at every given point of time. And here you will see the values written, the two main values which we keep looking in the capacitor, which is the capacitance value and the voltage withstanding capability. So, if you see in this, you see that it is a 2200 microfarad capacitor and it can withstand up to 450 volts DC. Okay. And these are other numbers which you will find which indicate the tolerance values. It can go from minus 50% to plus 100%, so on and so forth. Depends upon the capacitor and the make of the capacitor and things like that one. So, apart from this, you can also find still higher capacity capacitors, but it will be along those lines. So, generally the higher capacity capacitors, the one which is supposed to store energy as a buffer, they are generally electrolytic capacitors. The non-polarized capacitors are generally used for decoupling, to see that the average current in that particular lead or the particular wire is 0, and also for frequency tuning applications to determine the frequency of a particular circuit element. These are things for which the non-polarized capacitors find applications. The next topic that we shall discuss is the inductor, which is the second storage element which stores the kinetic energy. So far we had a look of capacitors of various sizes and types. Before we go on to the next topic, that is the inductors, I would like to mention that the capacitors have the unit called farads with a letter symbol F. So, you saw that on all the capacitors the nameplate reading shows farads, but it is prefixed by certain other Greek symbols like micro, pico, nano, so on and so forth, because most common capacitors have symbols written like this, called microfarad, which represents 10 to the power of minus 6 farads, nanofarad, which represents 10 to the power of minus 9 farads, picofarads, which represents 10 to the power of minus 12 farads. These three symbols, that is these three units, are the most common that you would come across in most of the capacitors. Of course, you could have other intermediate units, but these are some of the most common that you will come across. You have to just be aware of them. So, now we shall come to the next topic, which is the third component in our list, which is the inductor. We saw that the capacitor stored the potential energy. So, inductor stores the kinetic energy. So, what is the analogy? And like in the case of the capacitors, the inductors are also dynamic components, meaning they can store the state, in this case the flow would be the current, and it can have a memory. Like the capacitor had voltage as the memory, it can have current as the memory or the history. So, it can remember the currents, it can remember the current as a state variable, and it stores of course the kinetic energy. Consider this particular diagram here. You see that there is water flowing, a flowing mass of water. There is a wheel with some blades connected to the wheel, and the wheel rotates anticlockwise as shown here. And how does the wheel rotate? The rotation of the wheel is by virtue of the fact that there is energy stored in the flowing mass of, or the flowing body of water, and that impinges on these blades and causes the wheel to rotate. So, the flowing mass of water has some energy, has some stored energy. A vehicle which is moving has some stored energy. A person who is walking has some stored energy, which is the kinetic energy by virtue of it being in motion. So, it is that energy that we are talking of, and it is that energy which the inductor stores equivalently in the case of the electric circuits, and what is flowing is the current. So, the energy stored by virtue of current flowing is the kinetic energy which is stored in the inductor. So, the dynamic equations in the case of the inductor, like in the case of capacitor, very similar. You will see the voltage across the inductor is equal to L into di by dt, that is the differential of the current which is flowing through the inductor. Putting it the other way, the inductor current is equal to 1 by L integral of V dt. Notice again here the occurrence of this inductor, which means that it can store the state value. It has memory, it can store the history of what? Of the current. In the case of the capacitor, it was the voltage, because it was the voltage it was equal to 1 by the integral of I dt, but in the case of the inductor, it is the current which is equal to 1 by L integral of V dt. So, current is the state variable in the case of the inductor, it is the current which is causing the energy to get stored, unlike in the case of the capacitor, which was the voltage which was causing it to get stored as potential energy. So, what is the energy storage equation? In the capacitor, it was half CV square, V was the state variable, it was the potential. So, the potential energy was stored. In the case of the inductor, I is the state variable, I is the kinetic, the flow, the kinetic energy being stored in the flow, which is half L I square, as you see here on the screen. Inductor also comes in different types based on the core materials. We have the air core inductor, the ferrite core inductor, silicon steel core inductor, and also it can be categorized based on applications, the continuous applications, the low frequency applications, the switching applications which are more common in switched mode power supplies, filter applications which are used for removing the harmonics, things like this. The symbol for the inductor is as shown here. It is shown as coil, because generally the inductor is manufactured with some coils wound around a core, or it could be showed as a coil with a horizontal bar which indicates the presence of a core, and if the core is not there, it could just be without the line which indicates it is a air core. But this symbol without the line is also used for with core, with air core, and all those things, saturable, so on and so forth. One should note that if one is talking of a saturable core inductor, sometimes in the literature you will see a symbol which is like that. Sometimes you will also see symbol with double line for the core. Okay. These are the various symbols that you will find in the literature, but in general the basic symbol is the curved surface, the curved lines indicating the coils in an electric circuit. The inductor is having a unit called Henry, denoted by the letter symbol H. And like in the case of the capacitor, it can be microhenry, which represents 10 to the power of minus 6 Henry, millihenry, which represents 10 to the power of minus 3 Henry, or just henries. Okay, these are two common denominations of the units, the microhenry and the millihenry. You can also have nanohenries and other denominations depending upon the application. Now, let us see some practical real world inductors. You see here, this is a practical real world inductor. You have these two terminals coming out here, and there is a core here and the two coils here. Of course, here for handling the current rating, these two coils are paralleled. You see that these two wires are paralleled here, taken out here, the other two ends parallel and taken out here, but it can also be as well just one coil here. Let us see few other examples of the inductor here. Look at this frame here, there are various components. This is an E core, one half of the E core. This and this together forms the total core. In fact, this will go into this core, and this is called the bobbin. On this bobbin, we wind the wires, the copper wires. These are copper wires which are wound. Okay. And after winding, you take this core, put it like that, and assemble it in this manner. So, this becomes an inductor with a ferrite core. So, this is a ferrite core. Okay. You have one end of the winding here, another end of the winding here, goes through this coil, there is a bobbin, this bobbin is fitted into the core, is a ferrite core, ferrite EE core. You can also have different types of cores. This is a met glass type of core, this is called a CC core, goes from the geometry, this is a CC core. This is another ferrite core called the pot core. This has two halves, you have the bobbin here, on the bobbin is wound the copper wire and then it is placed within the pot core like that, and then you enclose the bobbin. So, you have the core enclosing the bobbin and flows through the coils. Okay. So, this is how the inductor has to be manufactured, and it is basically dependent upon the following equation. So, you have L, which is equal to mu naught mu r n square AC by L m. So, this is the inductor equation. You see that the inductor is proportional to n square, it is proportional to cross section area of the core, the cross section area of the core, and it is also proportional to the magnetic path length of the core, inversely proportional to the magnetic path length of the core, and it is also proportional to mu r, the relative permeability of the core material, and of course, this is mu naught, which is the permeability of air, which is 4 pi into 10 to the power of minus 7 Henry per meter. So, this mu naught mu r together is called the effective permeability mu E, and that is what is generally adjusted in the core in the type of the core material, or if the core material has a very high permeability, you try to adjust the material by introducing air gaps, and there are various methods in which you try to adjust the effective permeability. So, this is of course the basic equation in trying to get the value of the inductance, the core cross section area and the magnetic path length into account. Let me show you a typical power supply board, and let us try to identify the components and see how it is placed in the PCB, so that you get an idea of the various components that go into a practical circuit. Now, this is a practical printed circuit board. This is in fact an SMPS, a working switched mode power supply. Okay. We have the outputs, and here is the input. This is followed by a capacitor, is the aluminum electrolytic capacitor. Here you see 3 capacitors, which are the non-polarized capacitors. There is a board here. There is a piggyback board which is riding on the big motherboard. You see ceramic capacitor here, it's a transistor. There is a potentiometer here, and a whole lot of resistors inside here in the boards, on the board, and you see the power devices mounted on the heat sink here, and then gradually if I move this board here, what comes into focuses are some pot cores. This pot core is used as a transformer. These pot cores are used as inductors. Again, some electrolytic capacitors for the output. The pot cores here are the ferrite pot cores, and they are normally for high frequency applications. They can be used for applications ranging from 20 kilohertz to 100 kilohertz, and special cores even up to 300 kilohertz and further on. If you want to use for low frequency applications like 50 hertz applications, one has to use not this ferrite material, but the silicon steel material. Mu metal type of material can also be used for intermediate frequency range applications like 400 hertz to 1500 hertz and such. These pot codes can be used right from 20 kilohertz to 100 kilohertz, and in fact you have special ferrite codes which can go even up to 300 kilohertz, so on and so forth. Okay. So, these components here arranged on the printed circuit board with just the function of power supply here will give you an idea of how the physical components are mounted onto the board and used in practice.